Hello students. So now I am solving a few important problems on wave optics, and let us move to the first problem. So before solving the problem, first you have to read the problem thoroughly, and in any problem section in physics particularly, if you take a problem section, so you have to remember three important points. One is you have to go through the problem thoroughly. Then the second point is you have to list the given values, and third point is write the relevant formula to find out the unknown value. So in the problem some unknown value will be asked, and you have to write the relevant formula. You just have to recall the formula, and sometimes you need to modify the formula to get the required answer. So these are the three thumb rules, and even in exam also, even if you don't know how to answer a particular problem, try to understand the problem first, list the given values. If you remember, write the relevant formula. Even if you don't know how to solve the problem, if you write this much, you get at least 1 mark. So whenever you are solving the problem section, my advice to all the students that you have to solve the problem thoroughly, completely, with the proper unit, with the proper labeling. If you have a diagram related to this problem, so with this suggestion, I would like to start this problem section. First problem is two coherent sources of intensity is I and 4I produces interference pattern on a screen. Calculate the intensities at a point on the screen where the phase difference equal to pi by 2, B is path difference equal to lambda. So here they have given in one question pi by 2, which is phase difference. In the B part, they have given lambda, which is path difference. As I told in the video classes, that you must know the relation between phase difference and path difference, how to convert a path difference into phase difference, and how to convert a phase difference into path difference. It is not really a difficult part, very simple. If you take one complete cycle, which is equivalent to the wavelength of a wave, which is called lambda, and if the path difference between two waves is equals to the length of one cycle, that is lambda, which is equivalent to phase difference 2 pi, that is 360 degree. So if phase difference is pi by 2, then path difference is obviously lambda by 2, sorry, lambda by 4, because pi by 2 is 90 degree. So in this way you have to remember the relation between phase difference and path difference. Then in this problem they have given two values. One is intensity of first wave is I, second one is intensity of second wave, which is 4I, and they have given phase difference in one problem A, and another question B they have given a path difference lambda. Based on this, you have to calculate the resultant intensity. Let I1 is equal to I1 means intensity of first wave, I2 is a intensity of second wave. So here when phase difference equal to pi by 2, in this case we have to write the formula for resultant intensity IR. IR means resultant intensity. The formula is I1 plus I2 plus 2 root I1 I2 into cos phi. 2 is outside the root, remember this. And here given values are I1, in place of I1 you have to put I, in place of I2 put 4I. These are the two given values. 2 root in place of I1 I, in place of I2 4I into cos pi by 2. Cos pi by 2 is 0. This, in this way, this whole term get eliminated. This whole term becomes 0, because 2 root I into 4I into 0 equal to 0, leaving only I plus 4I, which is equals to 5I. This is the answer for A. Then we go to the second one, the path difference equal to lambda by 2. So when path difference equal to lambda, then the equivalent phase difference is 2 pi. So resultant intensity equal to, so resultant intensity IR equal to, again you have to write all the same values, but in place of this cos by 2 you have to write cos 2 pi, for because in B question the path difference is given lambda and the path difference is equivalent to phase difference 2 pi, then you have to write the value 2 pi here. So I becomes I as it is, this will be remain same. 2 root I into 4I means 4I square. When it comes out of the root, it becomes 2I. 2I multiplied by 2 equal to 4I into 1, because cos 2 pi value is 1. So if you add all these, then you get 9I. This is the answer for B question. In this way, you have to solve the problem. The very important thumb rule is go through the problem thoroughly, understand the problem. Then if you understand the problem thoroughly, it is almost half done. Then afterwards you have to list the given values, then write the appropriate formula. Substitution and calculations are the last part. Now moving on to problem number 2. In Young's double slit experiment, the distance between two slits is found to be 0.5 mm and the screen is placed 1.2 meter away from double slit. If the separation between any two bright fringes is 1.44 mm, find the wavelength of light used. Go through the problem thoroughly. In Young's double slit experiment, you have to recall two important formulas that I am going to explain it in the later section of this problem. But before that, you have to write the given values. The distance between two slits is found to be 0.5 mm, which means this is the value of small d. But you have to write it in meters. 0.5 into 10 to the power of minus 3 meter. And screen is placed 1.2 meter away from the double slit, which means this is a value of capital D, which is already given in meters. There is no need to convert it. If the separation between any two bright fringes, separation between any two bright or dark fringe is nothing but fringe width beta. The value of beta is given here, 1.44 into 1.44 into 10 to the power of minus 3 meter, because the value given is in millimeter. You have to convert it into meters. Recall the definition. The distance between any two bright fringes or dark fringes is nothing but, or which is called as, fringe width. And according to the formula, fringe width beta is equal to lambda d by small d, where lambda is wavelength of light used, capital D is distance between screen and slit, and small d is distance between two slits, separation of two slits. Then you have to solve the this equation for lambda. Therefore lambda equal to beta d upon capital D. Small d is given 0.5 mm, capital D given 1.2 m meters, beta 1.44 mm. The question is you have to calculate the value for wavelength. Therefore lambda equal to this formula you have to take here. Beta value is 1.44, beta value is 1.44 into 10 to the power of minus 3 into small d value is 0.5, which is given into 10 to the power of minus 3 meter. Given value is 0.5 mm and converted value is 0.5 into 10 to the power of minus 3, which is in meters, divided by capital D, 1.2 meters. Then the answer is 0.6 into 10 to the power of minus 6 or 600 nanometer. This is your correct answer. So this formula is very important. Beta equal to lambda d by small d. From this formula you come to know that fringe width is directly proportional to wavelength of light used. Fringe width is directly proportional to the distance between slit and screen, and fringe width is inversely proportional to slit separation. As we increase the slit separation, then the beta value will decrease. If you increase the lambda value, wavelength of light used, beta fringe width also increases. Capital D, distance between slit and screen, if you increase it, then the fringe width also increases. Then we go to the third problem. In this problem, Young's double slit experiment, while using light of wavelength 6600 angstrom unit, the fringe width is found to be 0.6 into 10 to the power of minus 3. If the distance between slit is reduced to one-third of its initial value, then what should be the wavelength of light to get the fringes 1.5 millimeter wide? Now, how to list the given values? The wavelength of light used 6600 angstrom unit, which is equal to 6600 into 10 to the power of minus 10 meter. Beta, which is given here, the fringe width is found to be 0.6 into 10 to the power of minus 3 meters. Then initial value of that slit width, we have to assume it that it is equal to small d. Then after reducing it to one third, then the new slit width becomes d by 3, because in the problem they have given that if a slit is reduced to one third of its initial value, so small d is a initial value and one third of d is a reduced value. You have to recall the same formula, fringe width beta equal to lambda d upon small d. This is for initial value. I am writing the same formula which I have used in the previous problem. Beta is equal to lambda d upon small d for initial value of d. Then I am writing the same formula for this reduced value, beta dash. I call it as a beta dash because whenever you change the value of small d, there is a change in the fringe width also. So now I call it as beta dash because the d has changed to d dash. So d dash is equal to small d by 3. This is for reduced value of a small d. Then you have to take the ratio. If you take the difference beta minus beta dash, then you will be having two unknown variables, small d and capital D. Then you can't get the answer which is asked in this problem. To get the answer, you have to take the ratio. By taking ratio, you can eliminate some common factors, like capital D is present in both formula, small d is present in both formula. So in this way you can eliminate these values. If you take the ratio beta equal to lambda d upon small d, beta dash equal to lambda dash d upon d dash. What is the value of d dash? It is equal to d by 3. Then if you solve it, all these common factors like capital D and small d get eliminated, leaving beta upon beta dash equal to lambda upon 3 lambda dash. If you solve it for lambda dash, which is equal to beta dash upon beta into lambda by 3, then you have to put all the values. In place of beta dash is given. What should be the wavelength of light used to get the fringe 1.5 mm wide? ಅಂದ್ರೆ ಈ ಡಿ ವ್ಯಾಲ್ಯೂ ಏನಿದೆಲ್ಲ, ಇನಿಷಿಯಲ್ ಡಿ ವ್ಯಾಲ್ಯೂ ಏನಿದೆಲ್ಲ ಅದನ್ನು ಒನ್ ಥರ್ಡ್ ಮಾಡಿದರೆ ನೀವು 1.5 mm ಫ್ರಿಂಜ್ ವಿಡ್ತ್ ಇರುವಂತ ಇಂಟರ್ಫರೆನ್ಸ್ ಫ್ರಿಂಜಸ್ ಅನ್ನ, ಇಂಟರ್ಫರೆನ್ಸ್ ಪ್ಯಾಟರ್ನ್ ಅನ್ನ ನೀವು ಪಡಿಬೇಕಾದ್ರೆ ಯಾವ ವೇವ್ ಲೆಂಗ್ತಿನ ಲೈಟ್ ಅನ್ನ ನೀವು ಯೂಸ್ ಮಾಡಬೇಕು ಅನ್ನೋದನ್ನ ಕೇಳಿದಾರೆ ಅವರು. ಈ 6600 ಆಂಗ್ಸ್ಟ್ರಾಮ್ ಯೂನಿಟ್ ಲೈಟ್ ಇನ್ನ ಯೂಸ್ ಮಾಡಿದ್ರೆ 0.6 ಇಂಟು 10 ಟು ದಿ ಪವರ್ ಆಫ್ -3 ಮೀಟರ್ ಫ್ರಿಂಜ್ ವಿಡ್ತ್ ಸಿಗ್ತದೆ. ಬಟ್ ಇಷ್ಟು ಫ್ರಿಂಜ್ ವಿಡ್ತ್ ಸಿಗಬೇಕಾದ್ರೆ ಆಮೇಲೆ ಡಿ ವ್ಯಾಲ್ಯೂ ಏನಿದೆಯಲ್ಲ ಸ್ಲಿಟ್ ಸಪರೇಷನ್ ಅದನ್ನ 1/3 ಮಾಡಿದ್ರೆ ಯಾವ ಪರ್ಟಿಕ್ಯುಲರ್ ವೇವ್ ಲೆಂತ್ ಇರೋ ಲೈಟ್ ಅನ್ನ ನಾವು ಯೂಸ್ ಮಾಡಬೇಕು ಅದನ್ನ ಕೇಳಿದ್ದಾರೆ, ಲ್ಯಾಂಬ್ಡಾ ಡ್ಯಾಶ್ ಅನ್ನ ಕೇಳಿದ್ದಾರೆ. So in this way you have to substitute the values of beta dash 1.5 into 10 to the power of minus 3. Lambda value is given 6600, angstrom unit is given, but you have to convert it into meter by multiplying 10 to the power of minus 10, then divided by original value of fringe width which is already given 0.6 into 10 to the power of minus 3 meter, then this factor 3. Then if you solve it, then you get 5.5 into 10 to the power of minus 7 meter. You can cross check by doing some calculations at your end. ಸೊ ಕ್ಯಾಲ್ಕುಲೇಷನ್ಸ್ ಭಾಳ ಇಂಪಾರ್ಟೆಂಟ್. ಬಹಳಷ್ಟು ಸ್ಟೂಡೆಂಟ್ಸ್ ಏನು ಮಾಡ್ತಾರೆ, ಇಲ್ಲಿವರೆಗೆ ಬಂದು ಈ ಕೊನೆ ರಿಸಲ್ಟನ್ನು ಬರೋಕ್ಕೆ ಸ್ವಲ್ಪ ತೊಂದರೆ ತಗೋತಾರೆ. ಆಮೇಲೆ ಇನ್ನೂ ಕೆಲವು ಸ್ಟೂಡೆಂಟ್ಸ್ ಏನು ಮಾಡ್ತಾರೆ, ಇದ್ರ ವ್ಯಾಲ್ಯೂ ಇದ್ರ ಫಾರ್ಮುಲಾ ಗೊತ್ತಿದ್ರು ಈ ಪ್ರಾಬ್ಲಮ್ ಸಾಲ್ವ್ ಮಾಡಕ್ಕೆ ಬರಲ್ಲ ನನಗೆ ಅಂದ್ಕೊಂಡು ಇದನ್ನ ಹಾಗೆ ಬಿಟ್ಟೋಗ್ಬಿಡ್ತಾರೆ. ಹಾಗೆ ಬಿಟ್ಟು ಹೋಗ್ಬಾರ್ದು. ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಆಗಿ ಈ ಪ್ರಾಬ್ಲಮ್ ಸೆಕ್ಷನ್ ಬಂದಾಗ ನೀವು ಪ್ರಾಬ್ಲಮ್ನ ಓದ್ರಿ, ಗಿವನ್ ವ್ಯಾಲ್ಯೂಸ್ ಅನ್ನ ಬರೀರಿ, ಒಂದು ಫಾರ್ಮುಲಾ ಬದ್ಬಿಡ್ರಿ, ನಿಮ್ಗೆ ಅಟ್ಲೀಸ್ಟ್ 1 ಮಾರ್ಕ್ ಅದು ಸಿಗುತ್ತೆ. ನೀವು ಏನು ಬರಿದೆ ನಂಗೆ ಇದು ಪ್ರಾಬ್ಲಮ್ ನಂಗೆ ಸಾಲ್ವ್ ಮಾಡಕ್ ಬರಲ್ಲ ಅಂತ ಬಿಟ್ಬಿಟ್ರೆ ನಿಮಗೆ 0 ಮಾರ್ಕ್ಸ್ ಬರುತ್ತೆ. ಸೊ ಥಿಂಕ್ ಪಾಸಿಟಿವ್ಲಿ. Now moving on to the fourth problem. I read the problem. In the two-slit experiment with monochromatic light, the fringes are obtained on a screen placed at some distance d, capital D, from the slits. If the screen is moved 5 into 10 to the power of minus 2 meter towards the slit, the change in fringe width is 3 into 10 to the power of minus 5 meter. If the distance between the slit is 10 to the power of minus 3 meter, calculate the wavelength of light used. When you go through this problem, again as I told, you try to understand the problem. They are doing the experiment with two slits. They are performing the experiment on interference phenomena, and the distance between slit and screen is capital D. It is unknown value. They are not given the any value for it. Then if the screen is moved 5 into 10 to the power of minus 2 meter means 5 centimeter towards the slit. When screen is moved towards the slit, this D value will decrease. If screen is moved away, then this total D value will increase. You have to focus on that particular keyword, whether it is towards the slit or away from the slit. If it is towards the slit, definitely D will decrease. So how much? Then whenever this D value changes, so there is always change in fringe width. So they have given the change in the fringe width 3 into 10 to the power of minus 5 meter. If the distance between a slit is 10 to the power of minus 3, because they are doing the experiment with two slits, means there is a separation between two slits. That value they have given here. Separation between two slits is 10 to the power of minus 3. That is small d. They have given small d. Then they are asking us to calculate the wavelength of light used. Now you have to recall the formula. Fringe width beta equal to lambda d upon small d, where the distance between a slit and screen is capital D. Then you have to write the same formula. One time you have to write this formula for fringe width for this D value. When this D value is reduced by this much, by 5 centimeter, then there is a change in the fringe width. So then I call it as beta dash. So beta dash equal to lambda d dash. I call d dash because d has now changed to new value after reducing the distance by this much. I call it as a d dash. Then there is a change in the fringe width. That fringe width will be called as b dash, beta dash, sorry. So when the distance between slit and screen is d dash equal to, it will be reduced by this much. So that means the d minus 5 into 10 to the power of minus 2 meter is the value of d dash. Then if you write the change in fringe width, change in fringe width is also given. Change in fringe width means beta minus beta dash. It is not beta by beta dash. Change in fringe width means beta minus beta dash. Whenever this value increases, beta also increases. because beta is directly proportional to lambda, beta is directly proportional to capital D, beta is inversely proportional to small d. So as this value decreases, the beta also decreases. So that is why I am taking beta minus beta dash, not beta dash minus beta. What is the value of beta? Lambda d upon small d, minus the value of beta dash is lambda d dash upon d. Then take out the common factor if possible. Lambda upon d is a common thing. Then leaving d minus d dash. Then you have to write the value of d dash inside the bracket. D minus of d minus 5 into 10 to the power of minus 2. So here d and d get cancelled, leaving this expression. Beta minus beta dash is already given here, 3 into 10 to the power of minus 5. Lambda that you have to calculate, d get cancels, leaving only 5 into 10 to the power of minus 2. I have written here, divided by a small d value. Small d value is given here, 10 to the power of minus 3. Then if you solve this equation for lambda, then lambda becomes 3 into 10 to the power of minus 5 into 10 to the power of minus 3 divided by 5 into 10 to the power of minus 2. When you solve it for lambda, you have to multiply these two, and then you have to divide this multiplication by this 5 into 10 to the power of minus 2 factor. So I have written here. So then after doing simplification and calculation, then you get to 0.6 into 10 to the power of minus 6 meter. This is your final result. But remember one thing, you have to recall a relevant formula. The relevant formula is lambda d upon d, because this problem is related to fringe width. You have to immediately recall the formula for fringe width, beta equal to lambda d by small d. Now we move on to fifth problem. In Young's double slit experiment, the slits are separated by 0.5 mm and the screen is placed 1 meter away. It is found that ninth fringe, bright fringe, is at a distance of 8.5 mm from second dark fringe. Find the wavelength of light used. So this is very important problem. Once you solve this problem, then you will be having a lot of confidence in solving this type of problems. Here, after going through this problem, we will come to now one important information is that we have to recall the formula related to bright fringe and dark fringe. When bright fringe means maximum intensity, dark fringe means minimum intensity or zero intensity. So you have to recall the formula for bright fringe, then for dark fringe, any nth value. After that, we can put a particular value of the order of the fringe according to the problem. The slits are separated by 0.5 mm. This is a small d value. The screen is placed 1 meter away. 1 meter away. Don't get confused. It is placed 1 meter away. It is not moved. Okay. It is placed 1 meter away means it is the value of capital D. Then ninth bright fringe. Maximum intensity formula you have to write. While writing the formula for maximum intensity for nth order, you have to put the value of n here as 9. Then they have given the distance between ninth bright fringe from the second dark fringe. So this 8.5 mm is the distance of ninth bright fringe, not from the center of the bright fringe. It is from the second dark fringe. ಇದು ಈ ಪ್ರಾಬ್ಲಮ್ ನಲ್ಲಿ ಕರೆಕ್ಟ್ ಆಗಿ ನೀವು ತಿಳ್ಕೋಬೇಕು. ಏನಂದ್ರೆ ಯೂಶುವಲಿ ಏನಪ್ಪಾ ಅಂದ್ರೆ ಈ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಡಿಸ್ಟೆನ್ಸ್ ಗಳನ್ನ ನಾವು ನಾರ್ಮಲ್ ಆಗಿ ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ದಿಂದ ನಾವು ಮೆಜರ್ಮೆಂಟ್ ಮಾಡೋದು. ಬಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಅನ್ನು ಕೊಟ್ಟಾಗ ನೀವು ಕರೆಕ್ಟ್ ಆಗಿ ನೋಡ್ಕೋಬೇಕು, ಇದು ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ದಿಂದ ಮೆಜರ್ಮೆಂಟ್ ಮಾಡಿದ ಡಿಸ್ಟೆನ್ಸ್ ಅಥವಾ ಯಾವುದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಫ್ರಿಂಜ್ ದಿಂದ ಮಾಡಿದಂತ ಡಿಸ್ಟೆನ್ಸ್ ಅಂತಿಕೊಂಡು ಇಲ್ಲಿ ಕೊಟ್ಟಿದ್ದಾರೆ. ಸೆಕೆಂಡ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ದಿಂದ ಮೆಜರ್ಮೆಂಟ್ ಮಾಡಿದಾಗ ಎಲ್ಲಿವರೆಗೆ, ಸೆಕೆಂಡ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ದಿಂದ ನೈನ್ತ್ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ವರೆಗೆ ನೀವು ಏನಾದರೂ ಮೆಜರ್ಮೆಂಟ್ ಮಾಡಿದರೆ ದ ಮೆಜರ್ಡ್ ವ್ಯಾಲ್ಯೂ ಈಸ್ 8.5 mm ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. ಯು ಹ್ಯಾವ್ ಟು ಕೇರ್ಫುಲಿ ಅಬ್ಸರ್ವ್ ದಿಸ್. Now let us see this fringes. Bright, dark, like that. Alternate dark bright and dark regions are formed due to interference. So count here: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. But you have to count it from the central bright region. All the distances are measured from center of the central bright region. Assume that this is the central bright region. You have to count it as 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. X9 will be the ninth bright fringe from the center of the central bright fringe. So this is the distance X9. Then second dark fringe. How to measure the second dark fringe? Again you have to measure it from the center of the central bright region. After the central bright region, first dark region, then first bright region, then second dark region. So this is the distance. So this dark region X2, which is located from the center of the central bright region by X2 distance. If you subtract this distance, the distance of second dark fringe from the central bright region from the distance of ninth bright fringe from the center of the central bright region, that is X9. X9 minus X2 gives this distance. Yellow color ತೋರಿಸಿ ನೋಡ್ರಿ, ಏನು ಕೊಡುತ್ತಪ್ಪ ಅಂದ್ರೆ ನಿಮಗೆ ಈ ನೈನ್ತ್ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಏನಿದೆಲ್ಲ ಸೆಕೆಂಡ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ಇಂದ ಎಷ್ಟು ದೂರದಲ್ಲಿದೆ ಅಂತ ಕೊಡ್ತದೆ. ಆ ಪ್ರಾಬ್ಲಮ್ ನಲ್ಲಿ ಅವ್ರು ಕೊಟ್ಟಿರೋ ವ್ಯಾಲ್ಯೂ ಯಾವ್ದಪ್ಪ ಅಂದ್ರೆ 8.5 mm ಅಂತಂದ್ರೆ ಇದೆ. So this is the distance of ninth bright fringe from the second dark fringe. ಈ ವ್ಯಾಲ್ಯೂ ಕೊಟ್ಟಿದ್ದಾರೆ ಅವರು. So given values are small d equal to 0.5 mm. You have to convert it into meter. Then capital D equal to 1 meter. It is given here. Then let this X9 is the distance of ninth bright fringe from the central of the central bright region. Let X2 is this is the distance of the second dark region from the center of the screen or center of the bright region. Then the distance of ninth bright fringe, the distance of ninth bright fringe from the second dark fringe is nothing but the distance of ninth bright fringe from the central bright region minus the distance of second dark region from the central bright region. If you take the difference of X9 and X2, which gives this distance which is given in the problem. Then according to the condition for maximum intensity, so maximum intensity, the distance of any nth bright region, the distance of any nth bright region is equals to n lambda d upon small d. But I have taken xn ಅಂತ ತಗೊಂಡಿಲ್ಲ, ನಾನು x9 ಅಂತ ತಗೊಂಡಿದ್ದೀನಿ. ಯಾಕಂದ್ರೆ ಅವ್ರು 9th ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಬಗ್ಗೆ ಮಾತಾಡ್ತಾ ಇದ್ದಾರೆ. ಸೊ n ಬದಲಿ ಅಂತ ಹೋಗಿ ನಾನು 9 ಅಂತ ಹೋಗಬೇಕು ಅಷ್ಟೇ. 9 lambda d upon d. This is your first equation. Then the x2 is the distance of second dark fringe. This is the condition for dark region. n plus half into lambda d. ನೀವು ಬರೀ n lambda d ತಗೊಂಡ್ರೆ ಬ್ರೈಟ್ ರೇಂಜ್ ಆಗ್ತದೆ. n plus half lambda d upon small d ತಗೊಂಡ್ರೆ ಇದು ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ರೀಜನ್ ದಿಂದ ಯಾವ್ದಾದ್ರೂ nth ಡಾರ್ಕ್ ರೀಜನ್ ಎಷ್ಟು ದೂರದಲ್ಲಿದೆ ಅನ್ನೋದನ್ನ ನಿಮಗೆ ಮಾಹಿತಿ ಕೊಡುತ್ತದೆ. So again you have to put the value of n here. While putting the value of n in the condition for dark region, you have to be very very careful. If you are taking n plus 1 by 2, then you have to write 1 in place of second dark fringe. ಅಂದ್ರೆ ನೋಡ್ರಿ, ಇದು n plus half lambda d upon d ಅಂತ ತಿಳ್ಕೊಂಡಿದ್ದೇನಿದೆಲ್ಲ, ಇದು ಒಂದು ಜನರಲೈಸ್ಡ್ ಕಂಡೀಷನ್, ಡಾರ್ಕ್ ರೀಜನ್ ಗೆ ಇರುವಂತ ಒಂದು ಜನರಲೈಸ್ಡ್ ಕಂಡೀಷನ್. n lambda d upon small d ಇದೆಲ್ಲ ಇದು ಜನರಲೈಸ್ಡ್ ಕಂಡೀಷನ್ ಫಾರ್ ಬ್ರೈಟ್ ರೀಜನ್. ಬಟ್ ನೀವು ಬ್ರೈಟ್ ರೀಜನ್ ದಾಗೆ ಆಸ್ ಇಟ್ ಈಸ್ ಏನ್ ಕೊಟ್ಟಿರ್ತಾರೆ ಅದನ್ನ ವ್ಯಾಲ್ಯೂ ಹಾಕ್ತೀರಿ, ನೋ ಪ್ರಾಬ್ಲಮ್. ಯಾಕಂದ್ರೆ ಬ್ರೈಟ್ ರೇಂಜಸ್ ಆರ್ ಆಲ್ವೇಸ್ ಕೌಂಟೆಡ್ ಫ್ರಮ್ ದಿ ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ರೀಜನ್. ಬಟ್ ಇಲ್ಲಿ ಸೆಂಟ್ರಲ್ ಡಾರ್ಕ್ ರೀಜನ್ ಅಂತ ಇರುವುದಿಲ್ಲ. ಡಾರ್ಕ್ ರೀಜನ್ ಸ್ಟಾರ್ಟ್ ಆಗೋದೇ ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ರೀಜನ್ ಆದ್ಮೇಲೆ. ಆ ಕಾರಣಕ್ಕಾಗಿ ನೀವು n ಪ್ಲಸ್ ಹಾಫ್ ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಡಿ ಅಂತಿಕೊಂಡು ಈ ಫಾರ್ಮುಲಾನ ಯೂಸ್ ಮಾಡ್ತಿದ್ರೆ ಅವ್ರೇನಾದ್ರು ನಿಮಗೆ ಸೆಕೆಂಡ್ ಡಾರ್ಕ್ ರೀಜನ್, ಫೋರ್ತ್ ಡಾರ್ಕ್ ರೀಜನ್, ಫಿಫ್ತ್ ಡಾರ್ಕ್ ರೀಜನ್ ಅಂತ ಕೊಟ್ಟರೆ ನೀವು ಒಂದು ಮೈನಸ್ ಮಾಡಬೇಕು. ಒಂದು ಮೈನಸ್ ಮಾಡಿ ಆ n ವ್ಯಾಲ್ಯೂನ ಇಲ್ಲಿ ಹಾಕಬೇಕು. ಅವ್ರು ಸೆಕೆಂಡ್ ಡಾರ್ಕ್ ರೀಜನ್ ಅಂತ ಕೊಟ್ಟಿದ್ರೆ ನೀವು 2 ಮೈನಸ್ 1 ಇಲ್ಲಿ 1 ಹಾಕು, n ಈಕ್ವಲ್ ಟು 1 ಅಂತ ಹಾಕಬೇಕು. ನಿಮ್ಗೆ ಇನ್ನೊಂದು ಫಾರ್ಮುಲಾ ಹೇಳ್ತೀನಿ, ಯಾವುದಪ್ಪ ಅಂದ್ರೆ n ಮೈನಸ್ 1/2 ಲ್ಯಾಂಬ್ಡಾ ಅಪಾನ್ ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಸ್ಮಾಲ್ ಡಿ. ಈ ಫಾರ್ಮುಲಾನು ಯೂಸ್ ಮಾಡ್ಬೋದು ನೀವು. n ಪ್ಲಸ್ 1/2 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಸ್ಮಾಲ್ ಡಿ ಬದಲಿಗೆ n ಮೈನಸ್ 1/2 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಸ್ಮಾಲ್ ಡಿ ಯೂಸ್ ಮಾಡಬಹುದು. ನೀವು ಮೈನಸ್ ಸಿಂಬಲ್ ಯೂಸ್ ಮಾಡಿದರೆ ಇಂಥ ಕಂಡೀಷನ್ ಅಲ್ಲಿ n ಮೈನಸ್ 1/2 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಸ್ಮಾಲ್ ಡಿ ಅಂತ ಕಂಡೀಷನ್ ಯೂಸ್ ಮಾಡಿದರೆ ಅವಾಗ ಅವ್ರು ಏನ್ ಕೊಟ್ಟಿರ್ತಾರಲ್ಲ ಸೆಕೆಂಡ್, ಥರ್ಡ್, ಫೋರ್ತ್ ಏನ್ ಕೊಟ್ಟಿರ್ತಾರಲ್ಲ ಅದನ್ನೇ ವ್ಯಾಲ್ಯೂ ಡೈರೆಕ್ಟ್ ಆಗಿ ಹಾಕ್ಬಹುದು. n ಈಕ್ವಲ್ ಟು 2 ಅಂತ ತಗೊಂಡ್ಬಿಡ್ಬೋದು ಇಲ್ಲಿ. ಯಾವಾಗ ಇಫ್ ಇಟ್ ಈಸ್ n ಮೈನಸ್ 1/2 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಡಿ ಅಂತ ತಗೊಂಡ್ರೆ, n ಪ್ಲಸ್ 1/2 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಸ್ಮಾಲ್ ಡಿ ಅಂತ ತಗೊಂಡ್ರೆ ಇಲ್ಲಿ ನಿಮ್ಗೆ ಸೆಕೆಂಡ್ ಡಾರ್ಕ್ ಅಂತ ಕೊಟ್ಟಿದ್ರೆ n ವ್ಯಾಲ್ಯೂನ ನೀವು ಒಂದು ಕಡಿಮೆ ಮಾಡಿ ಇಡಬೇಕು. ಇಫ್ ಯು ಪುಟ್ n ಈಕ್ವಲ್ ಟು 1 ಇಟ್ ವಿಲ್ ಬಿ 3 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ 2d. Then you have to take the difference, x9 minus x2. x9 is 9 lambda d upon small d and x2 is 3 lambda d upon 2d. Lambda d upon d is a common. 9 minus 1.5, 9 minus 1.5 is 7.5. Then you have to solve it for lambda value. Lambda equal to ಏನು ಮಾಡ್ತೀರಾ ನೀವು, x9 minus x2 ಗೆ ಈ ಸ್ಮಾಲ್ d ನ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಬೇಕು. x9 minus x2 ಎಷ್ಟಿದೆ, 8.5 ಇದೆ. 8.5 millimeter ಇದೆ. You have to convert it into meter by multiplying 10 to the power of minus 3 multiplied by small d. Small d value is given. It is how much? It is 0.5 mm. You have to write 0.5 into 10 to the power of minus 3 meter divided by d value is 1 and 9 minus 1.5 is 7.5. Then if you solve it, it will be 0.566 into 10 to the power of minus 6 meters. This is the answer. So you have to practice this problem particularly several times and similar problems, then only you can understand better. Now moving on to the sixth problem. A beam of light consisting of two wavelengths 650 nanometer and 520 nanometer is used to obtain the interference fringes in YDS Young's double slit experiment. What is the least distance from the central maximum where bright fringes due to both wavelengths coincide? The distance of the screen from the slit is 1.2 meter and distance between slit is 2 mm. You have to go through this problem once again. Here they are using two light sources. One is 650 nanometer, then its reduced value 520. While doing the experiment on interference phenomena, so they get a bright fringe for 650 nanometer on one particular point on the screen. Then if they switch off this light source and switch on this second light source, so here is the given values, lambda 1 equal to 650 nanometer and lambda 2 is equal to 520 nanometer. Capital D distance between slit and screen is 1.2 meters and the separation between two slits is 2 millimeter. So now if you use lambda 1, that is 650 nanometer, if this light is used, then you are having some bright region, nth bright region. ಎಷ್ಟನೇ bright region ಅಂತ ಗೊತ್ತಾಗಲ್ಲ, ಬಟ್ ಯಾವುದೋ ಒಂದು bright region ಈ P ಪಾಯಿಂಟ್ ನಲ್ಲಿ ಫಾರ್ಮ್ ಆಗ್ತದೆ. Then if you use 520 nanometer light, then you are again getting the some bright region, nth bright region. ಎಷ್ಟನೇ bright region ಅಂತ ಗೊತ್ತಾಗಲ್ಲ. ಸೊ ಅದು ಮತ್ತೆ ಪಾಯಿಂಟ್ P ನಲ್ಲಿ ಫಾರ್ಮ್ ಆಗ್ತದೆ, which is again coinciding with the earlier bright fringe. So question is very simple. 650 nanometer light ಯೂಸ್ ಮಾಡಿದ್ರೆ ಯಾವುದೋ ಒಂದು ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ P ನಲ್ಲಿ ಫಾರ್ಮ್ ಆಗ್ತದೆ. 520 ನ್ಯಾನೋಮೀಟರ್ ಈ ಲೈಟ್ ಯೂಸ್ ಮಾಡಿದ್ರೆ ಯಾವುದೋ ಒಂದು ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಮತ್ತೆ P ನಲ್ಲಿ ಫಾರ್ಮ್ ಆಗ್ತದೆ. Both are coinciding. Then you have to find out what is the distance of this point P where two bright fringes due to these two lights are coinciding at a certain point P from the center of the screen, that you have to find out the distance between this between P and C. So for any nth bright fringe, the formula is very simple: xn equal to n lambda 1 upon small d. I am writing it for lambda 1. Generalized formula is like this: xn equal to n lambda d upon small d. You have to write this formula for lambda 1. ಫಸ್ಟ್ ನಾವು ಯಾವ್ದು ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಂದರೆ 650 ನ್ಯಾನೋಮೀಟರ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಐ ಕಾಲ್ ಇಟ್ ಆಸ್ ಲ್ಯಾಂಬ್ಡಾ 1. 520ಗೆ ಲ್ಯಾಂಬ್ಡಾ 2 ಅಂತ ಕರೆಯೋಣ. ದೆನ್ ಐ ಆಮ್ ರೈಟಿಂಗ್ ಇಟ್ ಫಾರ್ ಸೆಕೆಂಡ್ ಒನ್, ದಟ್ ಈಸ್ ಫಾರ್ 520 ನ್ಯಾನೋಮೀಟರ್. ಯಾಕಂದ್ರೆ ಇಲ್ಲಿ ಲ್ಯಾಂಬ್ಡಾ ಕೊಟ್ಟರೆ, ಕ್ಯಾಪಿಟಲ್ ಡಿ ಕೊಟ್ಟರೆ, ಸ್ಮಾಲ್ ಡಿ ಕೊಟ್ಟರೆ, ಬಟ್ ಎನ್ ಮತ್ತು ಎಕ್ಸ್ ಕೊಟ್ಟಿಲ್ಲ. ಟು ಫೈಂಡ್ ಔಟ್ ದಿ ಎಕ್ಸ್ ಎನ್, ದ ಡಿಸ್ಟೆನ್ಸ್, you have to find out first n. So here I am writing the same formula for lambda 2, the same formula here. Again n, in place of n I am taking n plus 1, in place of lambda 1 I am taking lambda 2, capital D, small d as it is. But I am taking n plus 1 in place of n. It's because whenever you use 650 nanometer, you are getting some nth bright fringe at point P. When wavelength of light is decreased from 650 to 520 nanometer, second time ನೀವು ಕಡಿಮೆ ವೇವ್ಲೆಂತ್ ಇರೋ ಲೈಟ್ ಅನ್ನು ಯೂಸ್ ಮಾಡ್ತೀರಿ. ಯೂಸ್ ಮಾಡಿದಾಗ ಈ n ವ್ಯಾಲ್ಯೂ ಏನಾಗ್ತದೆ ಅನ್ನೋದನ್ನ ನೀವು ಗಮನದಲ್ಲಿ ಇಟ್ಕೋಬೇಕು. ಸಪೋಸ್ ಇಫ್ ಐ ರೈಟ್ ದಿಸ್ ಫಾರ್ಮುಲಾ xn equal to n lambda d upon small d for small n value, ನೀವು ಅದನ್ನ ಫಾರ್ಮುಲಾ ರೀರೈಟ್ ಮಾಡಿದ್ರೆ you get n equal to xn small d upon lambda d. Here you will come to one conclusion that whenever this lambda value increases, n value decreases. When this lambda value decreases, this n value will increase. In this particular problem, wavelength of light used is decreased from 650 to 520. First time 650 use ಮಾಡ್ತಾರೆ, second time 520 use ಮಾಡ್ತಾರೆ. ಅಂದ್ರೆ ಕಡಿಮೆ ಆಯ್ತು wavelength. If wavelength of light used, if it is decreased, then definitely n will increase. ಹಾಗಾದ್ರೆ n ಎಷ್ಟು ಇನ್ಕ್ರೀಸ್ ಮಾಡಬೇಕು? n plus 1 ಮಾಡಬೇಕಾ, n plus 2 ಮಾಡಬೇಕಾ, n plus 3 ಮಾಡಬೇಕಾ ಅಂತ ಕ್ವಶನ್ ಅರೈಸ್ ಆಗ್ತದೆ. ಸೊ ಯು ಹ್ಯಾವ್ ಟು ರೀಡ್ ದಿ ಪ್ರಾಬ್ಲಮ್. ಲೀಸ್ಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಂತ ಒಂದು ವರ್ಡ್ ಯೂಸ್ ಮಾಡಿ ನೋಡ್ರಿ. ಇಲ್ಲಿ ಲೀಸ್ಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಂತಂದ್ರೆ ಈ 650 ಲೈಟ್ ಯೂಸ್ ಮಾಡಿದಾಗ ಯಾವುದೋ ಒಂದು ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಫಾರ್ಮ್ ಆಗ್ತದೆ. 520 ಯೂಸ್ ಮಾಡಿದಾಗ ಅವಾಗ n ವ್ಯಾಲ್ಯೂ ಏನಾಗ್ತದೆ? ಜಾಸ್ತಿ ಆಗ್ತದೆ. ಅಂದ್ರೆ ಲ್ಯಾಂಬ್ಡಾ ವ್ಯಾಲ್ಯೂ ಕಡಿಮೆ ಆಯ್ತು, n ವ್ಯಾಲ್ಯೂ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. For least distance, n will increase by least value. What is the least value in integer? 1. So you have to write it n plus 1. In place of n, you have to write it n plus. So into lambda 2 d upon small d. Then when these two distances are equal, then only the bright fringe due to 650 nanometer and another bright fringe due to 520 nanometer, both are forming at the same point P. So both are coinciding. ನೀವು 650 nanometer ಯೂಸ್ ಮಾಡಿದಾಗ ಯಾವುದೋ ಒಂದು ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಇಲ್ಲಿ ಫಾರ್ಮ್ ಆಗ್ತಿದ್ರೆ, 520 ನ್ಯಾನೋಮೀಟರ್ ಲೈಟ್ ಯೂಸ್ ಮಾಡಿದಾಗ ಯಾವುದೋ ಒಂದು ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ಅದೇ ಪಾಯಿಂಟ್ ನಲ್ಲಿ ಫಾರ್ಮ್ ಆಗ್ತದೆ. ಅರ್ಥ ಏನಪ್ಪಾ ಅಂದ್ರೆ, ದ ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ nth bright fringe due to 650, the distance of n plus 1th bright fringe due to 520, both are forming at the same point P, which means xn must be equal to xn plus 1. I am equating this. If you equate this, what is the value of xn? N lambda 1 d upon small d. Xn plus 1 is n plus 1 lambda 2 upon d. Equate it, then you get this equation. Then common factors like small d and capital D get eliminated, leaving lambda 1 upon lambda 2 equal to n plus 1 upon n. If you solve it for n plus 1 upon n, then you get 650 into 10 to the power of minus 9. This is the value of lambda 1. 520 into 10 to the power of minus 9, which is the value of lambda 2. If you take the ratio, n plus 1 upon n becomes 5 by 4. Then if you solve it for n, you get n equal to 4, which means The fourth bright fringe due to 650 nanometer is formed at point P. When you use 520 nanometer light, then n plus 1. N is 4. N plus 1 is 5. So the fifth bright fringe due to 520 nanometer light is also formed at the same point P. Then you can put this n equal to 4 in any one of these two equation. ಯಾಕಂದ್ರೆ xn ಮತ್ತು xn ಪ್ಲಸ್ ಡಿಸ್ಟೆನ್ಸ್ ಎರಡು ಒಂದೇ ಇರೋದ್ರಿಂದ n ವ್ಯಾಲ್ಯೂ ಅನ್ನ ನೀವು ಯಾವ್ದಾದ್ರು ಎರಡು ಇಕ್ವೇಶನ್ ಅಲ್ಲಿ ನೀವು ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದ್ರೆ then you get x. Then if you put these values, I'm putting this value in this expression, xn equal to n lambda 1 capital D upon small d. So it will be 4 into 650 into 10 to the power of minus 9 into capital D value is 1.2 meter divided by a small d value is 2 into 10 to the power of minus 3. Then you get 1.56 into 10 to the power of minus 3 meter. This is the least distance of this bright fringe due to 650 and 520 nanometer are coinciding from the center of the screen. So this type of problem is also very important for exams. So whenever this type of problem is asked, first value is n you have to find out first. After finding n value, put the value of n in any of these two equations, then you get the final result. Then we go to seventh problem. Yellow light of wavelength 6000 angstrom unit produces a fringe of width 0.8 millimeter in Young's double slit experiment. What will be the fringe width if light source is replaced by another monochromatic source of wavelength 7500 angstrom unit and separation of light is doubled? Then ನಿಮಗೆ ಎರಡು ವೇವ್ಲೆಂತ್ ಕೊಟ್ಟಿದ್ದಾರೆ, ಒಂದು 6000 angstrom unit, ಇನ್ನೊಂದು 7500 angstrom unit ಅಂತಕೊಂಡು lambda 1 ಮತ್ತು lambda 2 ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. Then which produces the fringe width lambda beta 1 ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ, beta 1 0.8 mm in YDS. What will be the fringe width ಅಂದ್ರೆ ಇನ್ನೊಂದು fringe width ಕೇಳ್ತಾರೆ beta 2 when this light source of 6000 angstrom unit is replaced by 7500 angstrom unit and the separation of light is doubled. Separation of light ಅಂತಂದ್ರೆ small d ಅನ್ನ ನೀವು 2 times ಮಾಡಿದಾಗ ಈ 6000 angstrom unit ಅನ್ನ ತೆಗೆದು 7500 angstrom unit light ಯೂಸ್ ಮಾಡಿದಾಗ ಸೊ ಫ್ರಿಂಜ್ ವಿಡ್ತ್ ಏನಿಲ್ಲ ಅದು ಎಷ್ಟು ಬದಲಾವಣೆ ಆಗ್ತದೆ ಆಗೋದಾದ್ರೆ ಅದ್ರ ವಾಟ್ ಇಸ್ ದ ವ್ಯಾಲ್ಯೂ ಆಫ್ ದಟ್ ಫ್ರಿಂಜ್ ವಿಡ್ತ್. ಗಿವನ್ ವ್ಯಾಲ್ಯೂಸ್ ಆರ್ lambda 1 6000 angstrom unit means 6000 into 10 to the power of minus 10 meter. Beta value given 0.8 millimeter or 0.8 into 10 to the power of minus 3 meter. Then for lambda 2 value it is 7500 into 10 to the power of minus 10 meter. Then they are asking beta dash if small d is doubled. This is the given value. Then for lambda 1 you have to write the formula beta is equal to lambda d upon small d. This is the formula for fringe width. ಈ fringe width ಫಾರ್ಮುಲಾ ಬರೆಯುವಾಗ ಇಲ್ಲಿ n ವ್ಯಾಲ್ಯೂ ಹಾಕಬಾರದು, n ವ್ಯಾಲ್ಯೂ ಬಿಟ್ಟು ಹಾಕಬೇಕು. n ವ್ಯಾಲ್ಯೂ ನೀವು ಹಾಕಿಬಿಟ್ರೆ ಅವಾಗ ಅದು ಡಿಸ್ಟೆನ್ಸ್ ಬರ್ತದೆ. ನೀವು ಲ್ಯಾಂಬ್ಡಾ ಅಪಾನ್ ಡಿ ಅಂತ ಅಷ್ಟೇ ಬರೆದ್ಬಿಟ್ಟು ನೀವು ಡಿ ಅನ್ನ ತೆಗೆದು ಹಾಕಿಬಿಟ್ರೆ ಅವಾಗ ನಿಮ್ಗೆ ಆಂಗಲ್ ಬರ್ತದೆ. ಈ ಕ್ಯಾಪಿಟಲ್ ಡಿ ಅನ್ನ ಈ ಲ್ಯಾಂಬ್ಡಾ ಅಪಾನ್ ಡಿ ಗೆ ನೀವು ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿಬಿಟ್ರೆ ನಿಮ್ಗೆ ಏನು ಸಿಗುತ್ತಪ್ಪ ಅಂದ್ರೆ ಫ್ರಿಂಜ್ ವಿಡ್ತ್. ಸೊ ಲ್ಯಾಂಬ್ಡಾ 1 ಗೆ ನೀವು ಈ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಬರೆದ್ರೆ ಬೀಟಾ ಬಿಕಮ್ಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಲ್ಯಾಂಬ್ಡಾ 1 ಡಿ ಅಪಾನ್ ಸ್ಮಾಲ್ ಡಿ. If you write the same expression for lambda 2, it will be beta dash equal to lambda 2 upon lambda 2d upon 2d. Then you have to take beta upon beta dash. You should not take beta minus beta dash. If you take beta minus beta dash, change in fringe width, but the values of capital D and minus D are not given here. So that is the reason you should take the ratio of beta and beta dash to eliminate any one of these values or both. Beta value is beta upon beta dash I am taking. I am just first I am writing the value of beta equal to lambda 1 d upon small d divided by beta dash lambda 2 d upon 2d equals to d and small d get eliminated, leaving to lambda 1 upon lambda 2 then beta upon beta dash becomes equals to 2 into, just I'm putting the value of lambda 1 here and lambda 2. Then you get the ratio 12 by 7.5. I'm taking these three zeros in this power. It becomes 10 to the power of minus 7. And if I take 7.5, then 10 to the power of minus 10 becomes 10 to the power of minus 7. So therefore, beta dash, if you solve it for beta dash, it will be beta into 7.5 upon 12, which is equals to 0.625 into 0.8 into 10 to the power of minus. So moving on to the eighth problem, there's two spectral lines of sodium D1, D2 having a wavelength approximately 5890 and 5896 angstrom unit. A sodium lamp sends incident plane wave onto a slit with a 2 micrometer. A screen is located 2 meter from the slit. Find the spacing between the first maxima of two sodium lines as measured on the screen. So you have to write the first given values. Two wavelengths are given, lambda 1 and lambda 2. Write the value of lambda 1 as 5890 angstrom unit as 5890 into 10 to the power of minus 10 meter. Lambda 2 value is 5896 into 10 to the power of minus 10 meter. And capital D is 2 meter, which is given in this problem, 2 meter. So here in this diagram I am showing how the distances of these bright fringes due to these two wavelengths are located. So first I am taking a first bright fringe due to the wavelength 5890, which is located at this point. The distance of this point from the center of the screen is x1. Similarly, when the light is used 5896 angstrom unit, then you get some bright fringe at this point, and the distance of this bright fringe due to the wavelength 5896 from the center of the screen is x2. So I am taking x2 greater than x1 because whenever the wavelength of light used is increases, the distance of the bright fringes from the center of the screen also increases. ಅಂದ್ರೆ ವೇವ್ಲೆಂತ್ ಆಫ್ ಲೈಟ್ ಅನ್ನ ನೀವು ಹೆಂಗೆ ಜಾಸ್ತಿ ಮಾಡ್ತಾ ಹೋಗ್ತೀರಿ, ಹಂಗೆ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ಗಳ ದೂರ ಡಿಸ್ಟೆನ್ಸ್ ಏನಂತ ನಾವು ಹೆಂಗ್ ಕರ್ತೀವಿ ಸೆಂಟರ್ ಆಫ್ ದಿ ಸ್ಕ್ರೀನ್ ದಿಂದ ಅದು ಸಹ ಸ್ಲೋಲಿ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತದೆ. ನೀವು ಹೆಂಗೆ ವೇವ್ಲೆಂತ್ ಜಾಸ್ತಿ ಮಾಡ್ತಾ ಹೋಗ್ತೀರಿ ಹಂಗೆ ದ ಡಿಸ್ಟೆನ್ಸ್ ಏನಿದೆಯಲ್ಲ, ಏನ್ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ಗಳ ಡಿಸ್ಟೆನ್ಸ್ ಏನಿದೆಯಲ್ಲ ಸೆಂಟರ್ ಆಫ್ ದಿ ಸ್ಕ್ರೀನ್ ದಿಂದ ಅದು ಸಹ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತಾ ಹೋಗ್ತದೆ. ಅದಕ್ಕೆ ನಾನು x2 ಅನ್ನ x1 ಗಿಂತ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ತಗೊಂಡಿದ್ದೇನೆ. ಸೊ ಇಫ್ ಐ ಸಬ್ಟ್ರಾಕ್ಟ್ ದ ಡಿಸ್ಟೆನ್ಸ್ x1 due to 5890 angstrom unit from the center of the screen from x2, which is a distance of bright fringe due to this wavelength 5896 angstrom unit, then you get a spacing between these two sodium lines, these two bright fringes due to these two wavelengths. Delta x ಅಂತ ಕರಿತೀನಿ ನಾನು. x2 minus x1 ಮಾಡಿದಾಗ ನಿಮಗೆ delta x ಸಿಗುತ್ತೆ. So using the condition, we know that the distance of nth secondary maximum. This is a single slit experiment. This is not an interference phenomena. This is a diffraction phenomena. Single slit ಅಂದ್ರೆ diffraction, double slit ಅಂದ್ರೆ interference. Since it is a single slit phenomena, so we have to apply the formula of diffraction. ಸೊ ಡಿಫ್ರಾಕ್ಷನ್ ನಲ್ಲಿ ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ರೀಜನ್ ಆದ್ಮೇಲೆ ಏನ್ ಬರುತ್ತಲ್ಲ ಬ್ರೈಟ್ ರೀಜನ್ಸ್, ಅವುಗಳನ್ನ ನಾವು ಏನ್ ಕರಿತೀವಿ, ಫಸ್ಟ್ ಸೆಕೆಂಡರಿ ಮ್ಯಾಕ್ಸಿಮಾ, ಸೆಕೆಂಡ್ ಸೆಕೆಂಡರಿ ಮ್ಯಾಕ್ಸಿಮಾ, ಥರ್ಡ್ ಸೆಕೆಂಡರಿ ಮ್ಯಾಕ್ಸಿಮಾ ಅಂತ ಕರಿತಾ ಹೋಗ್ತೀವಿ. ಬಟ್ ಸೆಂಟ್ರಲ್ ನಾಗೆ ಏನ್ ಬ್ರೈಟ್ ರೀಜನ್ ಫಾರ್ಮ್ ಆಗ್ತಿಲ್ಲ ಅದನ್ನ ಮಾತ್ರ ನಾವು ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ರೀಜನ್ ಅಥವಾ ಸೆಂಟ್ರಲ್ ಮ್ಯಾಕ್ಸಿಮಾ ಅಂತ ಕರಿತೀವಿ. ದ ಕಂಡೀಷನ್ ಈಸ್ ಇಟ್ ಇಸ್ ಟೋಟಲಿ ಅಪೋಸಿಟ್ ಟು ದಿ ಇಂಟರ್ಫರೆನ್ಸ್. ಇಂಟರ್ಫರೆನ್ಸ್ ನಾಗೆ ನಿಮ್ಗೆ ಎನ್ ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ ಡಿ ಅಂತ ಬರ್ತದೆ, ಬಟ್ ಇಲ್ಲಿ ನಿಮಗೆ 2n+1 lambda d upon 2d ಅಂತ ಬರುತ್ತೆ ಇದು ಡಿಫ್ರಾಕ್ಷನ್ ನಲ್ಲಿ. ಸೊ ದಿಸ್ ಇಸ್ ದಿ ಕಂಡೀಷನ್ ಫಾರ್ nth ಬ್ರೈಟ್ ರೀಜನ್ ಆರ್ nth ಸೆಕೆಂಡರಿ ಮ್ಯಾಕ್ಸಿಮಾ, ವಿಚ್ ಈಸ್ ದಿ ಕಂಡೀಷನ್ ಫಾರ್ ಜೀರೋ ಇಂಟೆನ್ಸಿಟಿ ಇನ್ ಇಂಟರ್ಫರೆನ್ಸ್. ಇಂಟರ್ಫರೆನ್ಸ್ ಒಳಗೆ ಜೀರೋ ಇಂಟೆನ್ಸಿಟಿ ಏನ್ ನೀವು ಕಂಡೀಷನ್ ಬರಿತೀರಿ ಅದನ್ನ ನೀವು ಇಲ್ಲಿ ಬ್ರೈಟ್ ರೀಜನ್ ಬರಿಬೇಕು. ಇಂಟರ್ಫರೆನ್ಸ್ ನಾಗೆ ಕಂಡೀಷನ್ ನೀವು ಬ್ರೈಟ್ ರೀಜನ್ ಯಾವುದನ್ನು ಬರೆದಿರ್ತೀರಿ ಅದನ್ನ ಇಲ್ಲಿ ಡಾರ್ಕ್ ರೀಜನ್ ಬರಿಬೇಕು. ಸೊ ಬೋತ್ ಆರ್ opposite. So xn equal to 2n plus 1 lambda d upon 2d is the distance of any nth secondary maxima. Then if I write this equation for lambda 1 and lambda 2, same expression, you have to put lambda 1 here, nothing else. You have to put lambda 2 in this expression. In case of x1, you have to write lambda 1, 2n plus 1 lambda 1 upon lambda 1 d upon 2d. Then for lambda 2, you have to write 2n plus 1 lambda 2 d upon 2d. Delta x equal to x2 minus x1, as I told here. Then delta x becomes 2n plus 1. 2n plus 1 capital D upon 2d is the common factor in these two terms. Take out the common, then leaving only lambda 2 minus lambda 1. Here we have to take n equal to 1. First bright maxima they have given here. Find the spacing between the first maxima. First maxima ಅಂತಂದಾಗ ನೀವೇ ಮಾಡಬೇಕು, ಇಲ್ಲಿ n equal to 1 ತಗೋಬೇಕು. If you put n equal to 1 and the value of lambda 2 and lambda 1 here, then the answer will be 9 into 10 to the power of minus 3 meter. Then coming to the last problem, in Young's double slit experiment, the slits are separated by 0.28 millimeter and the screen is placed at a certain distance from the slits. The distance between the central bright fringe and the fifth dark fringe is measured to be 1.35 centimeter. Calculate the distance between slit and screen. Given wavelength of light is 6000 angstrom minute. ಇದು ಸಹ ನಿಮಗೆ ಈ ಡಿಫ್ರಾಕ್ಷನ್ ಅಲ್ಲಿ ಯಾವ ರೀತಿ ನೀವು ಪ್ರಾಬ್ಲಮ್ ಸಾಲ್ವ್ ಮಾಡಿದ್ರಿ ಪ್ರೀವಿಯಸ್ ಪ್ರಾಬ್ಲಮ್ ಅನ್ನ, ಅದೇ ರೀತಿ ನೀವು ಇಲ್ಲಿ ಇಂಟರ್ಫರೆನ್ಸ್ ಫೆನೋಮೆನಾ ಯೂಸ್ ಮಾಡಿಕೊಂಡು ಪ್ರಾಬ್ಲಮ್ ಅನ್ನ ಸಾಲ್ವ್ ಮಾಡಬೇಕಾಗ್ತದೆ. ಇಲ್ಲಿ YDS ಅಂತಂದಾಗ ಇಟ್ಸ್ ಅ 2 slit experiment and slits are separated by 0.28 millimeter, means this is the value of small d. The distance between central bright and fifth dark fringe is measured to be 1.35 centimeter. ಅಂದ್ರೆ 5ನೇ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ಏನಿದೆಯಲ್ಲ ಸೆಂಟ್ರಲ್ ಬ್ರೈಟ್ ಫ್ರಿಂಜ್ ದಿಂದ ಎಷ್ಟು ದೂರದಲ್ಲಿದೆ ಅಂತಂದ್ರೆ 1.35 centimeter. Then you have to calculate the separation between slit and screen. Capital D you have to calculate. Write the given values. Lambda is given 6000 to 10 to the power of minus 10 meter. Small d is given 0.28 millimeter. Then look at this diagram. This is a 2 slit phenomena. So this is a 2 slit phenomena. Here the 2 slits are separated by a small distance. So when you use this wavelength 6000 angstrom minute, you are getting some alternate dark and bright fringe. Assume that at this point you are getting fifth dark fringe and that distance is 1.35 centimeter from the center of the screen as it is given in the problem. And we know that the distance of nth dark fringe, the distance of fifth dark fringe is given by x5 equal to 2n plus 1 lambda d upon 2d. So therefore the fifth dark fringe you have to take n equal to 4. You have to remember this thumb rule. Whenever you are using 2n plus 1 formula, 2n plus 1 lambda d upon 2d, there are two different versions. We can express this formula xn equal to 2n plus 1 lambda d upon 2d. We can express the nth distance. You can express the distance of nth dark fringe by using the formula xn equal to 2n plus 1 lambda d upon 2d. When you are using this formula 2n plus 1 lambda d upon 2d, then you have to write 1 minus value for dark fringe. ಅಂದ್ರೆ ನಿಮಗೆ ಏನಾದರೂ ಫಿಫ್ತ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ಡಿಸ್ಟೆನ್ಸ್ ಕಂಡುಹಿಡಿಯಲಿಕ್ಕೆ ಹೇಳಿದ್ರೆ ಅಥವಾ ಫಿಫ್ತ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ಡಿಸ್ಟೆನ್ಸ್ ಏನಾದರೂ ಕೊಟ್ಟಿದ್ರೆ ಅವಾಗ ನೀವು ಫಿಫ್ತ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ಅಂತಂದ್ರೆ ನೀವು ಡಾರ್ಕ್ ಫ್ರಿಂಜಿನ ಆರ್ಡರ್ನ ಇಲ್ಲಿ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕಾಗ್ತದೆ. ಫಿಫ್ತ್ ಅಂದ್ರೆ ಇಲ್ಲಿ 5 ಅಂತ ಯೂಸ್ ಮಾಡಬಾರದು. 2n plus 1 ಫಾರ್ಮುಲಾ ಯೂಸ್ ಮಾಡಿದ್ರೆ ನೀವು ಈ ಫಿಫ್ತ್ ಅನ್ನೋದನ್ನ 4 ಅಂತ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕು. ಇಫ್ ಯು ಆರ್ ಯೂಸಿಂಗ್ 2n minus 1 lambda d upon 2d, if you are using 2n minus 1 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ 2d ಈ ಫಾರ್ಮುಲಾ ಯೂಸ್ ಮಾಡಿದರೆ ಮೈನಸ್ ಅಂತ ತಗೊಂಡು ಯೂಸ್ ಮಾಡಿದರೆ ಅವಾಗ ನೀವು ಫಿಫ್ತ್ ಅಂತ ಆಸ್ ಇಟ್ ಈಸ್ ಅನ್ನ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ಬೋದು. ಎನ್ ಬದಲಿ ನೀವೇನು ತಗೋಬಹುದು, ಎನ್ ಬದಲಿ 5 ಅಂತ ತಗೋಬಹುದು ಡೈರೆಕ್ಟ್ ಆಗಿ. ಬಟ್ 2n ಪ್ಲಸ್ 1 ಲ್ಯಾಂಬ್ಡಾ ಡಿ ಅಪಾನ್ 2d ಈ ಫಾರ್ಮುಲಾ ಯೂಸ್ ಮಾಡುವಾಗ ಎನ್ ವ್ಯಾಲ್ಯೂನ ಒಂದು ಮೈನಸ್ ಮಾಡಿ ತಗೋಬೇಕು. ಇಲ್ಲಿ ಫಿಫ್ತ್ ಕೊಟ್ಟಿದ್ರೆ ಎನ್ ವ್ಯಾಲ್ಯೂನ 4 ಅಂತ ತಗೋಬೇಕು. ಇಲ್ಲಿ ಏನಾದ್ರು ನಿಮಗೆ 10th ಅಂತ ಕೊಟ್ಟಿದ್ರೆ ನೀವು ಎನ್ 1 ಮೈನಸ್ ಮಾಡಿ, ಅಂದ್ರೆ ಇದರಲ್ಲಿ ಒಂದು ಮೈನಸ್ ಮಾಡಿ ಎನ್ ವ್ಯಾಲ್ಯೂನ ಇಲ್ಲಿ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕು. ಸೊ ಇಲ್ಲಿ 10th ಕೊಟ್ಟಿದ್ರೆ ಇಲ್ಲಿ 9 ಆಗುತ್ತೆ, ಇಲ್ಲಿ 10th ಕೊಟ್ಟಿದ್ರೆ ಇಲ್ಲಿ ಅದು 9th ಆಗುತ್ತೆ. Then you have to substitute the values in place of x5. You have to write 1.35 into 10 to the power of minus 2. 2 into 4 plus 1 into lambda d upon 2d. 2 into 4 plus 1 as it is. Then you have to write the value of lambda 6000 into 10 to the power of minus 10 meter. And d value we don't know. Keep it as it is. 2. Then small value of d 0.28 into 10 to the power minus 3. Then if you solve it for capital D, ಈ D value ನೀವು ಸಾಲ್ವ್ ಮಾಡಿದರೆ then you get just cross multiplication. ಈ ವ್ಯಾಲ್ಯೂ ಏನಿಲ್ಲ ಇದನ್ನ ಇದಕ್ಕೆ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ರಿ. D equal to ಅಂತ ಬರೆಯುವಾಗ ಇಲ್ಲಿ ಏನು ಬರ್ದಿರ್ತಿಲ್ಲ ಇದನ್ನ ನೀವು ಡಿವೈಡ್ ಮಾಡಬೇಕು ಈ ವ್ಯಾಲ್ಯೂದಲ್ಲಿ. So 1.35 into 10 to the power of minus 2 multiplied by this value. 2 into 0.28 into 10 to the minus 3 divided by, you have to take this value 2 into 4 plus 1, 2 into 4 plus 1 into 6000 into 10 to the power of minus 10. Simplify and solve it, then you get 1.4 meter. So this is how you have to solve the problem. When very important thing is when you are using these type of formulas 2n plus 1 and 2n minus 1, you should remember that when you are using 2n plus 1 formula, then you have to take 1 minus. If it is a fifth, you have to take n value as 4. If you are using 2n minus 1 formula, then you have to take as it is. If it is a fifth one, you can take n equal to 5. So with this I am leaving. So you have to practice similar problems given in your textbook and try to solve maximum number of problems, because either problem or theory part is compulsorily appearing from this wave optics topic, and especially problem section has appeared many times. So I wish you all the best.